Hello, Saucer Java community. In today's session, we're going to look into the modern feature of Java called virtual threads. It's going to be mostly an overview report that should also encourage you to learn more about the recent Java concurrency features and features in general, and evaluate where you can leverage it. So in today's session, firstly, we'll briefly touch the traditional Java threading approach in server applications. Next, we'll explore the virtual threads feature concept and what it offers. We'll also run some code snippets and leave some time at the end to casually chat about the topic. So in traditional threading model, a thread is implemented by a thread class, and it's mapped one-to-one to an iOS, which is operating system thread. It's basically a thin wrapper around it. It's Java's unit of concurrency. It's run sequentially and independently alongside with other threads. So all statements in Java methods are executed within threads. Multiple threads can execute concurrently, and thread has a stack to manage local variables, method calls, and exception context. Stack traces provide developers with info about errors and about the origin of those errors, which is more important. And threads are friendly to tools like debuggers and profilers. So in this schema, let's remember it for a while. We have this one-to-one mapping. Next, before we go into the virtual threads, I would like us to look into like typical tasks a thread executes. So it's basically a story about IO-bound versus CPU-bound tasks. There are two types of tasks. If a task doesn't carry out many calculations, but it does a lot of input-output operations, it's called an IO-bound task. Since CPU is much faster than input-output buses, we have to wait a long time for a bus or device or network resource to be available for reading or writing. These kind of tasks, IO-bound tasks, can be handled well in an asynchronous way. The examples of such tasks you can see in this list below. And if task does a lot of operations using CPU, it's called a CPU-bound task. For example, image resizing is kind of a CPU-bound task because it recalculates the pixels from an original image, but only saves the results when it's ready. So the difference between IO-bound and CPU-bound tasks is not obvious, and not every task can be classified strictly to an IO or CPU bound. Like to resize an image, you have to keep the whole image in the memory. But if you transcode something like a video stream, it may actually take a lot of IO and CPU resources simultaneously. So with this in mind, let's get back to the traditional threading model and the challenges of it. It takes about 1 megabyte per thread in the memory. And it also takes some time to start an operating system thread. It seems not so significant, but if we multiply this time to thousands of threads, it becomes to be quite significant. And context switches that take place also take time, and the more the number of threads, the more frequent the switches are. Many threads may spend a significant portion of their life cycle in waiting for something like a network response. And this in turn leads to underutilization of the system resources. In the traditional thread per request approach, threads often block while waiting for I/O operations, like reading from a database or making a network call. When the thread is blocked, it occupies the operating system thread and preventing it from being used for other tasks. So this behavior results in inefficient resource utilization, and it can actually degrade the performance during high input-output operation times, wait times. To mitigate these blocking issues, developers use asynchronous programming paradigms that rely on callbacks or futures. However, these approaches introduce complexity and can lead to something like callback hell or difficult to manage code structures and making it harder to maintain and debug applications. There are modern frameworks to deal with that, and virtual threads is not there to substitute this approach. But that sounds more like a topic for separate sessions, and we're deliberately focusing on virtual threads in this session because virtual threads simply they actually simplify the programming model for concurrency, making it easier to develop and maintain by allowing developers to write code in synchronous way, which looks synchronous while being non-blocking actually under the hood. So a Java virtual thread, it's a feature finalized in JDK 21. And it was released a year ago. So now Java has two kinds of threads, platform threads and virtual threads. A virtual thread is also an instance of Java-lang thread. So the same parent type in this case, but it extends it. It is a lightweight compared to the platform threads, can be created faster and consumes much less memory. A virtual thread can run any code that the platform thread can run, and this thread is handled entirely by Java runtime. The Java runtime also can map many virtual threads to a small amount of platform threads. And debuggers also allow to step through virtual threads, show call stacks, and inspect variables and stack frames. So while a platform thread typically requires large stack size, like 1 megabyte per thread, virtual threads are implemented with a shallow call stack, which allows them to use significantly less memory. For instance, creating 10,000 of threads, platform threads, can consume around 10 gigabytes of memory, whereas the same number of virtual threads might only use about up to 5. And virtual threads are stored in the Java heap like other objects, which allows JVM to manage their memory more efficiently. So just to recall, to create a platform thread, now we know that it's just a traditional thread. It was like this, and it stays like this. Virtual threads is not there to substitute the traditional threads. But now we have this additional factor method called of platform to distinguish between the virtual and platform thread creation more clearly. So here's the way we start the platform thread. Here's another way to start it. And this is the way we used to take to actually submit a task to a pool of executor threads. And it just remains mostly as is, but there's this new cool feature in Java 21 that now the executor service is out closable, and it actually waits for all the submitted tasks to complete before exiting the application. So to create a virtual thread, we have another factory method, which is start virtual thread, and it also accepts a runnable. We can also assign a name to the virtual thread, because by default it's empty. And here's just another way to do the same. It's more interesting in the executor's service part, because for the virtual threads, we have this new executor, new virtual thread per task executor. So it's actually not a pool. It's a new virtual thread being created anytime you submit a new task to this executor service. So for execution, the Java virtual thread is mounted on a platform thread, which in this case is called a carrier thread. So each virtual thread is mounted on a carrier thread, and this carrier thread executes the virtual thread's code until it encounters a blocking operation. So when it encountering a blocking operation, the Java runtime detects this blocking change. This was the part of the huge refactoring they did to the JDK to support this. And examples of blocking operations include something like waiting for network responses, file reads, database queries. Actually, all blocking calls in JDK have been refactored to call something like yield in the new continuation class that they introduced. And they reworked the whole Java util concurrent network and IO packages to support this functionality. So what about the state of the thread when it's being unmounted? So upon detecting the virtual thread is blocked, Java runtime unmounts it's from the carrier thread. This means that the carrier thread is now released and can now be used to execute other virtual thread, improving overall throughput this way, and hence provides better resource utilization. So the state of the unmount virtual thread is preserved on the heap. This allows the virtual thread to be resumed later when the blocking condition is resolved. Like in this case, after waiting, it resumes, but on a different carrier thread. Sorry, misclicked. So once the blocking operation completes, the Java scheduler can remount the virtual thread onto any available carrier thread. And this remounting can happen on the same carrier thread or on a different one, as we see, depending on the system availability and scheduling decisions. So under the hood, this works as a fork join pool, not the same as the common fork join pool, a different one, and it uses first input, first output order. There are a few options to control the virtual scheduler settings. How many platform threads will be created per core, and the maximum number of carrier threads created by the scheduler. So we can control this using these JVM options. It all looks cool, but it has some caveats. So when switching to virtual threads in your application, you not only have to check that your own code support, but also that the third-party libraries support the Java 21 and virtual threads in order to guarantee efficiency and compatibility. So almost all the platform threads problems you may face are still there with virtual threads, like race conditions, deadlocks, visibility, shareability of the threads. But also that means that many existing solutions to ensure that your code is correct and safe are also the same, and you probably know them. However, I'd like to highlight some more caveats. A code example that you may have a problem with. When a virtual thread encounters a synchronized block and attempts to acquire a lock that is already held by another thread, it becomes what we call pinned to its carrier thread. And this means that the underlying platform thread cannot be released back to the pool for other tasks while the virtual thread is waiting on this lock. As a result, this can lead to thread contention and reduced throughput. In contrast, when using reentrant lock, a virtual thread cannot acquire the lock because it is held by another thread, and it can regain control of the carrier thread and return to a non-blocking state. So this allows the carrier thread to execute other virtual threads while waiting for the lock to become available. And this overall improves throughput and resource utilization. So the use of the synchronized code blocks is not of itself a problem, only when those blocks contain some blocking code. Generally speaking, I/O operations. It can be problematic as the carrier platform threads are limited resource, and platform thread spinning can lead to application performance degradation when running virtual threads without careful inspection of the actual workload that they execute. Well, in fact, the same blocking code in synchronized blocks can lead to performance issues even without virtual threads, with just the traditional ones. So revising the synchronized usage is one of the very few actions that libraries and projects will have to do to fully leverage virtual threads. So there are some scenarios in which virtual thread can be unmounted, cannot be unmounted during blocking operations because it's pinned to its carrier thread. One we've just took a look in, and another one is when it executes a native method. I think it's a rare one for most of the projects, but it's good to keep that in mind. So when a native method being executed, there can be the same situation, and that is because they wanted to restrict like any manipulations with the thread stack using the native C++ code, for example. So in the user code, we also must not make assumptions about how or when virtual threads are assigned to platform threads. At least not more than we make assumptions about how often platform threads are assigned to processor cores. Another caveat is that, well, it's actually an anti-pattern. You should not pull virtual threads. Never pull virtual threads. Instead, create a new virtual thread for even a small, short-lived concurrent tasks, just like shown in this example. So basically, the number of virtual threads this way should equal the number of concurrent tasks that you use them for in your application. As for the use cases for virtual threads, I found out that there's a general principle to that. So it can be generalized like this. Virtual threads can be used in applications that consist of a great number of concurrent tasks that spend much of their time waiting. And on this diagram, it shows how multiple virtual threads share a single platform carrier thread. We can see that, for example, the carrier thread executes virtual thread 2. Then you can see my pointer, right? Or not?
Yes.
Yes, we can.
Yeah, we can.
Here I have a fancy one. a laser. So here the virtual thread 2 is being executed. Then once it becomes blocked, virtual thread 1 is being executed. Then it goes waiting, and this one is waiting too, and it's time for the thread 3 to run. Then it goes waiting, and virtual thread 2 can do something in the meanwhile. So it's running, then this one's running, and so on and so forth. So this diagram illustrates the efficiency of this single platform thread executing the workload of 3 virtual threads mounted on it. So this way, we kind of fill in the gaps that the carrier thread would otherwise just spend for nothing. So virtual threads are not faster than platform threads. Those are not going to solve latency problems either. They just can allow more throughput, which means that you basically won't get faster, won't get the response faster for as a user, but you rather can serve more users simultaneously, providing the same speed of the response. This is one of the key takeaways, and another one is that virtual threads can significantly improve throughput when the number of concurrent tasks is high, like thousands, and there's actually a rule of thumb that the JDK authors suggest, like if your application doesn't have like 10,000 virtual threads or more, it is unlikely to benefit from virtual threads. But it can mean that either the load is too light and doesn't need better throughput actually, or you have not represented sufficiently many tasks to virtual threads. And the second one, the workload is not CPU bound. So in this case, having many more threads and processor cores won't help the throughput. So in summary, virtual threads simplify concurrent programming. They allow developers to write code in a straightforward manner, similar to synchronous programming, and they preserve a reliable thread per request style that is in harmony with the design of the Java platform, and at the same time, it helps to utilize the hardware resources better. So now let's go run some code snippets in the IDE.
Yeah, we have one question.
Yeah, sure.
Yeah, hello. Small question about the last statement about 10,000 of virtual threads. So is it means that, I know, how is it calculated? For example, if we have like, 10 platform threads or 10,000 platform threads, how is it related to amount of virtual threads?
So
Yeah, go on.
I'm not sure that I understood the question well enough, actually.
Yeah, just can you comment the last statement in previous slide?
The rule of thumb, right?
Yeah.
Well, I don't know how this was produced, but I can assume that with the current hardware, you can actually, and multiprocessor cores, you can actually execute a lot of simultaneous or concurrent operations, even if there's some IO involved, and it still be fast enough. So we can probably look at this as like if we have 10,000 concurrent users, for example, then we would like to try using virtual threads.
Okay.
So
Yeah, but if
that
we
is
have like couple of 100 user, it is most likely that we will not have any like performance improvements.
actually, I don't have a slide for that, unfortunately. I haven't included it, but let me put it this way. With migrating to virtual threads or just starting with them from scratch, you would better measure the application performance and see what you'll see.
Okay.
So that would be the best possible approach in this case, because still the feature is quite fresh and there's probably not much best practices established.
Okay. And from your experience, like did you use it in production, and what was the result?
So my experience is the compilation of this report, actually, because I was curious about the topic. I've never used virtual threads in the projects, so this is my first exploration of it.
Okay.
And this way, I would really appreciate if there's like anyone in this meeting that has some real experience and can share it. And we'll have a time for that just briefly. Let's go to the ID and we'll be up to the discussion.
We
One more, okay.
yeah, one more question. Oh,
I
comment.
just
I don't know.
yes, I just wanted to add that in Java 24, they added a JEP that would solve the synchronization block issue. So from Java 24, synchronization block will not cause thread ping.
Okay, yeah. It's still in preview, but of course it is there. So I didn't want to bring anything that is in preview yet to the table today. So of course there are things like structured concurrency that is also there. That is really interesting to explore if your Java version on the project is somehow this new. So let me share the IDE probably. I don't have much. I wish I had more. So this is just some snippets that we have seen in the presentation. Here, if we create, you can see the ID, right?
Yeah.
Yes.
Cool. Let me make it more readable for you. Is it better or worse?
Better, I guess.
Let's make it a bit smaller. So here, when we create the traditional threads and we print the, we just do the toString of the thread, which actually prints some things like, okay, we won't see it, but it prints something like thread ID, thread name, thread group, and when we create a virtual thread, well, actually, I don't like this scale because I don't see the code snippets well enough. Let's make it smaller. So when we create virtual threads and do the same here, what we had was the traditional ones, and here's was the virtual ones. We can see that the thread info also includes the carrier thread, and it's coming from this for join pool, this part. And it also has its own ID. And by the way, it doesn't have a name because, well, most of them doesn't have a name because this code doesn't set any. And we should be able to see, yep, there are some with the names. Just a small detail. Also, this was the way we created a pool and submitted tasks to it. And there was also an attempt to help with the time spent waiting by producing a completable feature that is executed in a separate platform thread. And we can see that when we run this piece of code, so actually submit this completable feature to the executor service, which is the fixed thread pool of 5, the number of active threads becomes 7 after there were 2 initially, some of the kind of system ones. So this was one of the attempts to help with the throughput. And then the virtual threads. This is just the basic stuff, and here we can see this code that can show us that the carrier thread is actually different after the virtual thread was waiting for some time. So IO bound operation simulates some IO blocking operation. In this case, it's just sleep. And we have a CPU bound operation. So this goes as part of this job. And for the job ID 5, we print the log just to see that some of the parts of the job were executed by a different carrier thread. If we run it like multiple times, of course, we can see different results because of the differences in the scheduling. We also can play with some comparison of the performance with simulated CPU-bound tasks and IO-bound tasks. And we can actually vary the amount of CPU work iterations and sleep millis and number of tasks that are being executed. And we can see that for the number of tasks, 1,000, the platform threads and virtual threads execute mostly the same if it's a CPU-bound task. And for the IO-bound tasks, virtual threads are much, much more efficient. And this is just an example of 1,000. We can exaggerate that, of course, to be something like maybe this big. Let's try. Oh, I'm not sure it's gonna play well. It's this amount. So what we've just seen actually brings us to another great conclusion, that virtual threads for the CPU-bound tasks are really not faster than the platform threads, but they are actually slower because there is some overhead for managing the virtual threads. And when it's just the CPU calculations, we can't gain any benefit from that. Well, I'm gonna stop it because with this amount of the platform threads, it's terrible. Let's see. Well, in this case, virtual threads did a bit better, but I think it's just within the boundaries of the deviation. Okay, let it run there, and let me get back to the slides. So right now, if you have anything to share for the community, let's share some thoughts. Like, how have you adopted virtual threads? Feel free to speak and share. Do you plan to try using virtual threads in your code, in your projects?
We have question or comment, I guess.
Yeah, hello everyone. So
That's
I
also
have
part of the discussion. That
I
works.
have some questions. First of all, thank you for a great presentation. It was clear that you wanted to bring your thought on the table about the virtual thread and why do we need them. I have two questions. First one, the question based on your personal opinion. So listening to this presentation and all what I know about the virtual thread, don't you think that virtual thread it's not like the best name suited for this feature? I have like inner feeling that this feature should be named like virtual task or something, because unlike the carrier thread or the platform thread, when it's actually mapped one-to-one to the actual physical thread, virtual thread is likely some amount of work that can be shared between all this physical thread between Java platform thread. So basically, I think it can't be named like a real thread because it's not like the representation of the real runner on a physical level. It's rather the task that should be consumed by another runner. I have the feeling that they choose this name just to have the more bigger audience, or I don't know, to show to show off a little bit. I don't know, but it's like my personal opinion. I just want to know if you share the same thought. And the second question, so we all know that there is two main problems related to concurrency. And the first one, you presented it very well, that there is IO and other waiting operation. And you bring us to this actually is the excellent solution to avoid this IO operation. But the second is actually the context switching. And the question is, maybe you heard about the situation, about that maybe those virtual threads management can slow down, can make the context switching, I don't know, like 5% faster, or I don't know, maybe 10% faster, because if we have, for example, 10,000 virtual threads, I believe that the context switching cases will be like much, like a lot, if we are using those features. So yeah, that's the question. Thank you.
Okay. So I think that the naming is actually works well with the existing paradigm in the Java library, because virtual thread actually extends well, it extends base virtual thread, but internally it extends the thread. So it's an instance of thread, and it would be weird to call it something like job, because, like, judging from the name, it's capable of executing something rather than being executed. So that also should play well for the compatibility, because anything that you could run on a thread can now be run in a virtual thread. I mean, you should assess if it's worth it, but you you are able to do that without probably any changes in the like the payload of your job that you want to run. So naming, I think it's fine. Then as for the context switching, so basically there's no context switching when you're like as a scheduler arranging the virtual threads to the carrier threads, because you have a pool of threads that are carrier threads. It's like a fork join pool dedicated specifically to the virtual threads, and the default number of carrier threads there is the number of the available CPU cores. And what the scheduler is doing, it's loading or mounting and unmounting the virtual threads to already started existing platform threads. So it's not the same context switching as when you deal with the platform threads directly. So I think that that's where they gain that benefit of the speed, and I think the feature exists in the first place at all. Okay, is there anyone who tried virtual threads in any project, like, or migrated to virtual threads? That would be even more interesting.
You could put pluses in the chat.
Just unmute and
or unmute, yeah.
tell us how great or how terrible that is.
We have raised hand. Yuri.
We use virtual thread to execute some HTTP calls mostly. It's a nice feature. It simplifies working with any I/O operation quite a lot, since you don't need to worry about your connection pool. You don't need to worry about some threads that are being used a lot, and basically right now it has limited support, because for instance Kafka client doesn't support virtual thread because they use a lot of synchronized blocks in their code, and so other popular clients do not support virtual thread at the moment, but I believe in the future it will be a huge change for the Java ecosystem, and it may bring us a little bit closer to what Kotlin has with their coroutines.
Thanks for sharing. Yeah, Kafka is something I was really curious about, if we could utilize virtual threads there. I don't know how well that plays when you actually need to acknowledge the message, and while you're not acknowledge that, you just not processing the next one. So yeah, I think that needs more discovery. But Kafka is something I would really like to see utilizing this, because I have just the feeling that it can be used for this type of processing. Is there anything in your mind that you expected to hear about during this session?
Yeah, Roman.
Yes, thank you for your presentation. I have one question about using, for example, volatile or atomic classes for synchronization, do we need to use it for virtual thread as well, or maybe virtual threads helps us to handle some cases when we can skip using volatile or atomic classes for some synchronization?
Well, there's really no explicit info about this, but I guess that all that has been true with the traditional threads, still true with the virtual threads. So it's like all the same rules, and even the thread local is now supported. There was a time during the preview when thread local variables were not supported by virtual threads, but now they are supported. There's really question if they are useful because like you can benefit from something like thread local when it's something that used by a thread in a pool, for example. But with virtual threads, that may be a bit of an overhead to have. So volatile and other like tools to deal with the concurrency are still valid.
Okay, thanks. And another question, our client decided to switch from Java to Kotlin. Maybe you know if we can use Java virtual thread in JVM executing Kotlin code. I mean, yeah, like using Java virtual thread, writing application using Kotlin. Can we use that feature in Kotlin?
I don't know for sure. I recall that Kotlin has something
Coroutines.
coroutine, yeah.
Yeah, but I think it's not
it's-
like virtual thread.
It's not the same. It's really not the comparable concept. So I can't answer this one.
Okay, thanks. Thanks, anyway. I'll check.
You know, one thing that I wanted to check that came into my mind lately or late, I wanted to spin up just a small Spring Boot application with like two REST controllers, the one that handles requests using traditional threads and the other one that handles using virtual threads, and try to load it using a JMeter, for example. And yeah, the service itself should simulate some
Right.
IO-bound operations in order to get some meaningful results, of course. And another test that and I can actually try and maybe attach the source code to the materials in the blog related to this session.
It would be great if you.
I'm curious, like, what if I configure Spring to use virtual threads to serve the requests, actually. So this service will be serving requests only using virtual threads. I believe that there can be a place for a service like that within some project areas. Maybe like an application to synchronize something in two data sources, and you want to do that in batches, for example, and launch a batch using like a REST endpoint. You provide the IDs or you provide the range or something like that, and then it does the mostly IO job. So that could be interesting, actually. Worth trying, I guess.
Yuri, do you want to add something?
I wanted to add about Kotlin. So Kotlin use their own scheduler. They implemented their own scheduler for coroutines, and they do not use virtual thread. But since it's a JVM language, you can probably use virtual threads from Kotlin as well. So from what I understand, the community is currently leaning to using Kotlin native coroutines rather than using Java virtual threads. And also, I wanted to add that there is a useful system property, which is called JDK trace pin threads. And when you set it to full, basically it will log every time a thread pinning event occurs. And it can be quite useful when you want to check whether your application is ready for virtual threads. Because if let's say you start your application and run some tests and see that in logs you have this events printed, it means that you probably should rethink whether to turn off it in production to avoid any disruptions in your service. And I added the name of the property to the chat.
Thank you. That's really useful. And on my part, I have this references slide at the end of the slide deck. So there's this "Dude, Where's My Luck" article by someone from the Netflix tech blog, and it actually describes their case when they investigated a deadlock in the environment where they had virtual threads running. Quite interesting one. As well as there's this video from the official Java channel that describes the topic probably even better than me. So I think now, before we wrap up, let's just take a moment to appreciate the existence of this community. Thank you all for joining this meeting or watching in the recording.